Alrighty. Um, so third derivative here, we are demoing Lab 11. As you can tell, we're all in the same room actually. We're just
No, Neurali's in San Francisco.
well, actually, my bad, Neuralink from San Francisco.
It's not like, 2 feet behind.
2 feet behind me, her voice in the background. No idea. No,
So
who's that?
Verso Maxer.
Jeez. So that being said, in this lab, you essentially implemented and compared four different matrix multiplication approaches, a CPU baseline, a naive GPU kernel, a tile shared memory GPU kernel, and an optimized CU BLAS version. The goal was to measure performance across increasing matrix sizes and understand how GPU parallelism improves computation speed. By benchmarking and visualizing the results, we could see how each method scales and why GPU accelerated matrix multiplication is dramatically faster than a traditional CPU implementation. So if you're hearing that, you're like, what does that mean? We are here to show you. So we had a very rudimentary version made in Colab, which I am sharing here. This is not the final version, but it kind of introduces the idea of what we were trying to do. So we did use the NVIDIA SMI. We wrote some code to work on CPU matrix multiplication, to work on the naive CUDA kernel, to work on the optimized CUDA kernel, to work on the CU BLAS implementation,
Plus.
cuBLAS. We benchmarked all the implementations here. We plotted the speed ups here so you can take a look at the comparisons. Um, but Steve, I'm going to pass the floor to him because he's going to talk a little bit more about the improvements that he made and what changes he made. So that being said, floor is all yours, Steve.
Hello, hello. Yeah, yeah, that's what I meant. This is gonna be a buggy. Uh, yes, it's gonna be buggy regardless. There's a lot of stuff that we still don't understand, and it's kind of pissing me off in particular. But it's also like it's quite annoying. So I already copied like a few speed up plot result, like some plot results, but they don't matter. So, anyways, where are we at? So, uh, I feel okay. Can I nano this? I'd be surprised if I can. Oh, I can. All right, you can ignore most of the like output results. I'll try to make this a bit understandable. So initially, the idea was we would just like call write file on a cell, and then we just write up off the code like this. These things are like these are relatively simple. This is just matrix multiplication. Written in C. I just allocate data. Sorry, allocate space, right? Like, oh no, it's just memory allocation. Yeah, yeah, yeah. Malloc. Yeah, yeah, yeah. And then we clock results, multiplied, and yeah, we got the execution time. We do the same with the naive version, the naive kernel. Like, the difference here was these two lines. So these two lines turns out to be, I think, absolutely crucial for every single um CUDA global program. And basically, it's just finding the row in the column based on like the block dimension, which is something I don't think we understood yet. Like, there's something we just had to go and look up online because it was like block dim is block dim is just kind of weird. I think over time we knew that it was initialized at 256, and it's probably better to keep it that way. I think I put it at 512 sometimes, but overall, it's like this these two is these two lines matter a lot, and we can't just do like a four somewhere here, apparently. Not sure I understood it correctly, but once again, same stuff. Um, reading the bytes. Oh yeah, this just okay. Reading the bytes. creating events, recording the start and stop times. Apparently, this is better than blocking on your own. And yeah, more stuff. And a tile version, we just tile the results on a 16 by 16, and then we multiply all like in every 16 tile. So it's like a 16 by 16, right? And then you have 256 values, and you multiply on those 256 values at once. That's the idea. That's why, like, remember when I was saying that like the block was 256? Yeah, it works on a similar idea here. Anyways, copy memory. Okay, we'll talk about this very soon, but allocating data, getting, oh, this is building random numbers. Like starting stopping event, nothing interesting. Q plus is apparently bugged. We will also talk about that later, but I mean, Q plus did make our life a lot easier at a very non-trivial cost we'll talk about later. Cost we'll talk about later. Uh, so this is the main one, I believe. Yeah, so we call subprocess, we define like the ends, we calculate like all of the outputs, like the check output here. This is a bit complicated, but at the same time, I wanted to print out results because otherwise, it doesn't make sense. Like this is like you get the output, right? Because yeah, because the way you wrote the output, remember on the previous version was that you put a bunch of like outputs and then you have to like sort the output. So that's yeah. That's what we did. And yeah, this so we got this sort of output, which is already surprising because Q plus is already 10x faster than the tiled like version. I'm not sure why the tiled version is that better. It may or may not have something to do with the fact that I own a GPU that can run 256 slots at once, which is why tiled can do like 256 at once, right? Another thing that really surprised me is the difference between 256 and 512 here. I think something happened here with how, yeah, like as you can see, a lot of the output is very inconsistent for some reason. I like we don't get it. The rest doesn't matter. Yes, probably just whatever. So obviously that's not a good way to write code, if only because of the fact that you're supposed to like have them in separate folders and then call them. And you never write code on a Python notebook if you want, consistency. Like I'm not blaming anyone, but So huh? Oh, wait, did I mess up? Hmm. Let me try. Oh, I think I messed up. Oh, well, that's why. No, no, I think this is .c and .co, but I'm pretty sure I saved okay. Yeah, I think I messed up something here. We'll figure it out later. But I think that's just a .so that you can use. No, whatever. cdlib. Oh, there we go. We'll figure out what they are later. I am not sure. So a lot of things I learned, and a lot, like I feel like this is a week early compared to when we have to submit this thing, but that's much better we got this out way. So I may or may not understand this correctly. A lot of this is copied from the likes of Stack Overflow, just so you know, and whatnot. So apparently this matters a lot because then it lets you know that you have an error beyond just, oh, you have an error. And this is just for the kernel, and this is just for the CUDA itself, I believe. Something interesting. Something I learned also doing coding is that writing code like this looks much better. Um, like having these comments to, oh wait, no, this is a convolution kernel. Okay, not the one to show first. Conf, no, matrix, right? Yeah. Oops, wrong one. So this is a tiled version of multiplication. There's just a like few differences. First of all, like apparently saying as tile width is more understandable in tile. Uh, very normal for loop. You just multiply things. But apparently, it's much better to sync threads here. Like you sync as you go. And also apparently, well, this is true. Like you don't want to send the data to. This is actually true later on for CNN, but you don't want to send the data to like the GPU and then send it back. This doesn't really matter because this is just for benchmarking and we're only doing like t equals one. So there's no like second step or third step. Doesn't really matter. But for CUDA, like apparently it's the same thing. But also I believe we need to write like an exposed version. So this is a CUDA definition essentially, and this is the C one. So extern C. I remember seeing this in the lecture near the end, and I was like, "What the hell is extern C?" Remember? It was like you need to know extern C so that you can transfer from CUDA to C. Yeah, that's the one line where it's like, "Why the hell is it there?" So it turns out this is C. Like all of these are okay. These things such as like C definitions. But these are like allocating memory to CUDA. This is copy pasting to CUDA and sync, which I believe has something to do here. You multiply, like you said, the triple brackets or whatever, and then you copy your memory back and then freeing the space. Otherwise, you get leaky memory or whatever. I don't remember what happened, but I think I forgot the sign and it was for it. Conflict. The C files are actually not here. I'm actually surprised. So this is just like the very boring version of convolution. That's interesting. I think some files are. Did I lose them? Hmm. Or are they here? Yeah, you're not gonna be able to read them. Um, I know I compiled them somewhere, but I don't remember how I got like these files in particular. Because there are a bunch of .cus, which then got compiled to .cs. Apparently, the lib. Eh, figure it out later. So if I go to nano main, benchmarks, of course. This is really helpful for compiling these files. Oh, there we go. Okay, I remember now. Yeah, they are just named like this. Well, I'm pretty sure they got an extension, but at some point, apparently it doesn't matter. Because initially I think we should have used like NVCC. We didn't end up using NVCC, so we just like C make this, which is apparently just make. This is taken from my experience in Matrona, so hmm, don't remember what happened exactly. But we check the CPU, we compile all of the matrix programs and this one. This is for the convolution one. And then you're gonna start, seeing some horde stuff later on. Getting the output. getting output, running some benchmarks. Here are the ends, so these should look similar. And then the benchmark convolution. So tw 28 and 32 wasn't necessary, but only one was really necessary, but you'll see why it matters. This one turns out to not matter a lot. I'll just explain what happens. This is just convolution. We use MNIST style and Seyfarth style. You'll see why we need that. And then we just run these shared libraries at the end. This one is for testing the matrix library. This one says it's a convolution library. And this one is I hate myself and I want to do something to show off, I guess. So what happens? Oh, you can ignore this error. So it's just a 404 on the CNN library, which is well, it's not even a CNN library. It's a MNIST one. So first, so I can show you in real time. I can show you later on. But first of all, you know what? I can show you in real time. Probably I should. Python benchmarks.py. There we go. First of all, check whether a GPU exists. I have a 4090 laptop, waste of money and burns your computer, but 12.4, so everything's fine. It compiles of these, I believe, and it compiles the convolution programs, which are these two. Why does it show like horizontal? Then it runs multiplication benchmarks. There will be some really interesting results to show. Takes a bit. Oh, there's also a result CSV. All right, let's wait here. As you can see, this is oh the CPU took 35 seconds. That's why it took so long. So I mean the very obvious thing is even for n equals 256, we already see CPU being much worse. Like obviously if we go back to like n equals 2 and the CPU makes like it's much more optimal because why would it not? Like you have to send all the data over and back and the PCI bus is slow, like you said. But we can already see from 250 like 256 that the tiled approach is like 2x already faster. And the cuPlus is very slow. I don't get why it's so slow. This is a bug that I was mentioning. Like it is like it gets faster with higher N2, which is definitely a bug. I don't know why this bug exists. I have no idea. I'll figure it out later on. But even then, like tiled shows better results, and I think that's just because I guess you get like a full block of data sent in instead of having to consecutively send data in. No, no. For YouTube Plus was still slower, but it's only like 2x, right? Whereas this is like 60x slower. Like this is like okay, zooming in always okay. No. That's too much. Okay, this is like 893 microseconds. Microseconds. This is 76,000. I I don't even know how it got 76,000 not like microseconds, but it we we'll figure it out later. Oh yeah, I think this wasn't really helpful to show because this matrix multiplication convolution was where it was probably more helpful. And we decided to show like Sifar versus Sifar and Ennuis versus the bigger ones. And even for the smaller ones, like as you increase what the yeah, this is what I meant when I said it feels a bit buggy. But anyways, so the higher the image size, the higher the speed up. And equally interestingly, the higher the filter size, the higher the speed up. Like obviously there are exceptions here, But I'm not even sure if this is an artifact of terrible uh measuring time. So if it's just bad multiplication or if it's something else. At the same time, we can see that like for higher MNN, like the GPU starts being much faster. Like this is definitely an artifact somehow, but you can see how like the GPU's like time increases very slowly. So if you take the max of the three, which will probably make our life easier, like this is 1,000, 1,600, 1,800, 2,300, and I have no idea how this only got like 1,000. But we can see like a very slow incline now, whereas the CPU starts from 3 to 18,000, which is a very much steeper like N. And I can actually tell you a virtual experience, which is way more helpful than just this. But I'll talk about this later. So then generating plus turns out the plus aren't that interesting, and these artifacts turned out to like be a much bigger issue. Compiling libraries is just the SO that you've seen. If you go back to, do I have it on main? No, this is for TNM. Whatever. It's not too interesting. It's just compiling to SOs. Um, testing the library. Not. Oh, yeah. This is just to ensure that the libraries are shareable. So something that we learned a lot, like well, not a lot, but like again and again, is the compiling. Uh, the NVC. Remember one where it's like there was a bunch of stuff, like a bunch of flash you have to remember. Like I copy pasted a whole explanation. Let me bring it up. I was like, there's no way that there's so much stuff to think. Let me find it. Oh, there we go. This one. So let's copy paste. We'll talk about the rest later too. So just remember, yeah, very important like stuff. So I believe this one means you send it to C instead of like the NVCC. This is to ensure that I believe I don't really remember. This this is something like position independent code. I know that much, but apparently all I knew is that it's required for GCC to compile correctly. Wait, is this GCC or G plus plus? We use GCC. Yeah. Because it's C, so it's GCC. G plus plus uses is a compiler for C plus plus. Does that make sense? Okay. Yeah, and this is a very important one because otherwise you would compile it's not a shareable, but like an executable, and that is absolutely unusable for Python. This just means level two optimization. This got me into a very understatement of a rabbit hole where I learned like optimizations levels actually matter and they do some Kurtz shit, you know. And then that show just means output, I believe. Yeah, output file. Nothing interesting. But this is very important for me to like understand. And that's how I got out of hellhole. And the bigger hellhole is the CNN because I was like, I'm gonna kill myself and I want to do something interesting with my life. So while these two were doing more fun stuff, such as interviewing people, I was like, let's try doing something that makes me hate my life. And here we are. Can I can I please go to line one? Hello? Oh no, I can't do that. There we go. All right. Nothing interesting. This just calls the path, the CNN path. And this will look absolutely painful, and I will do my best to explain what's going on. Because I don't think I get what's going on. I'm just yapping. Uh, a multiple pointer. Like this just goes back to your explanation on how uh we have to use pointers. I mean, this is defining like C-types arguments, so it's nothing interesting. Um, I believe this is very necessary for the stuff shown below. These are just definitions to ensure that it doesn't explode. Right, 2D convolution. Shout out to CSCI 566, whatever class that is. What's the name of the class? It's like deep learning network, you know? Like it taught me CNN. I was like, damn, this is fun. Um, this is actually simple, well, not simple, but like it's Python stuff. So if you wrote Python, you knew this. Just define the stride, the padding, and what a case for, I forgot. The weights, yeah, the weights. Just you have to just the output of it should be one normally, I believe. So it's like defined as the input plus two times the padding because you have to pad on both sides, right? Minus one divided by stride. Oh wait, no. Yes. Never mind. And then plus one because you start to count until it ends. Uh, normally you also have to round down, but that's for later. Output is just a bunch of zeros for now because it's just like a very normal convolution model, nothing interesting. There you go. ReLU, I mean, it's like flat line straight up. I would have thought about leaky ReLU or something else, but I was like, nah, I don't want to deal with it. I just want to understand what's going on. So pooling, normal technique, you consider your pool size and you pick the maximum value as that. Um, so let's say you have a 28 by 28, right? And you pick a pool of like size of two, like then you have every two by two. You pick the maximum value of the four values in the two by two, and then you get and then you get a 14 by 14 of maximum values. This is to I don't remember. This is just to ensure that the most important features come through. There we go. Fully connected layer, normal CNN stuff, just send values over. Submax, not sure why we end up using submax. I think we just ended up using ReLU. Loss, I believe this is, yeah, cross entropy. And an SGD update. Very average CNN stuff. First layer, since from the convolution of 32 by 32. It's 32 of 32 with 3 by 3 padding. Cool. Into a ReLU into a not full. I think it was stride or something. Uh no, it's one stride, one padding. Okay. So literally just copy pastes the whole thing over with a ReLU and then a max full. And you just continue. You flatten the output, do a fully connected and get a submax, which is just a normal sigmoid on the back end. Actually, I wonder why I use submax and not ReLU there, but that's for later. Just reshaping. Here, there's a very important point where you want to identify. I'm sure somewhere, but but at some point you want to identify the arc max of the max pool so you can target only that for SGD. Very important technique. And then just training. A very simple self-forward. Computing the losses and whatever. This was where the bug was. We used Jan LeCun's MNIST, which didn't work. Downloading the files, like opening the data, normalization, very normal stuff. Normalization matters a lot. I think without normalization, like the data set just jumped like insane places. And technically, this is not normal. This is just resizing into a uniform. You know the idea. Um, Evaluation, very simple stuff. You just argmax and get the correct values divided by the sum of values. Yeah, no, the total value, samples. to any hyperparameters. Oh yeah, another bug that kind of annoys me is that it doesn't really print every like. I think it got suppressed when I caught in main, but that once again something I'll figure out later. Training, epoch loss, game results, something that we can feed into like TQDM. We didn't have time to feed into like TQDM. I hate TQDM. I hate how annoying it is. I don't hate it. It's very good. And yeah, if it works, you get results, which no, do not save. And yeah, this print every 100 gives you like these losses. And yeah, you get less and less losses. If I had time, I'd actually run. You know what? Let's try this Python CNN.py. Should work. Yeah, so the print got suppressed. I am fair. Yeah, the print got suppressed by main.py. Okay. Cool. So nano to the conf main.py. Not main, Jesus. Benchmarks. I really should rename this main actually. This is supposed to be a main. Sweet. Sounds like a very fancy name. Once again, we compile everything. So we already talked about how like we ran off this, right? I think I I think just gonna scroll down and show the end, like very simple. Yeah, so we ran these for the matrix for like benchmarks, generating plots, compiling everything. Where did I run CNN? I forgot. Hmm. It's definitely somewhere. Hmm. Oh, there you go. Why did I write it here? Jesus. My God, I'm terrible at writing code. Yeah, I should have moved this down here. This is not the best idea. I feel like at the time it was just like, oh yes, let's just write run command because it makes me look cool. Well, I should have done something else. Um, yeah, so the output was actually not suppressed, which surprised me a lot. Hmm, didn't know that. Also, it was limited to 1,000? Was it 1,000? No, not this one. I think main limited it to 1,000. Or maybe that's just me. No, it was 1,800 too. So much stuff to do. I mean, technically, this doesn't even like properly compile yet. Like, if we use PyTorch for this, we would have more control on like the torch files, what we want to download, what we want to do, whether we get to save, like whether we can early stop, right? Like, you wouldn't train for only 3 epochs at 1,800. Uh, I think I just picked 1,803 epochs because it was fast and we just didn't have time to test. But actually, we shouldn't have made this video, just sitting here for like 3.5 minutes watching this run. Probably should have ran this before. Yeah. Yeah, I mean, even then you see some interesting stuff, right? Like by here, you're starting to see some like starts to fat line. So at this point, I was like, yeah, sure, but probably should have wrote something to only save the best. But I didn't get to learn that, so um, yeah, it stops. But even then, you can see that it still goes down a tiny bit. So what I suspected would happen on Epoch 4 is it's probably going to drop to like 0.09, zero point 0.1. And that's where we should see most of the like it actually flatlining. Even then, we see very high confidence in the predictions more often than not, and we can see a marked decrease when it's uncertain. So that's a lot. Um, I'm pretty sure I can because the prediction is cross entropy, so I definitely can find like a list of full predictions for every one of them, but time limitations and I suck at CUDA. So what did we learn? We all suck at CUDA. I don't know who made this possible. I hate CUDA, but I can see why it makes you $500,000 a year. You know what? Fair enough. Bro, this is why we're poor, like we just don't learn how CUDA works. Okay, well, funny backstory. You know what? Because funny backstory. So the biggest thing I learned is actually not the biggest thing I actually learned is not on this project, funnily enough. So we have another thing we did. I would try to be very short with the understanding. Yes, I know this is disgusting. Um, VS Code, this is not, I don't know. Yeah, this is just not your, yeah, average version. But anyways, what was trying to say? So we were working on another project in our in the other lab where one of the things we have to do is we have to show that Erdos smart this guy. No, he's Polish. I don't even know how to say his name. Like Erdos is actually easy. It's like Scissor Meredy. There we go. This guy this guy basically said that some this guy basically said that well no, it's still conjecture, but this guy basically said that either the sum set or the product set has to be too big. And we wanted to figure out a way to disprove it. So we build like all you have to understand is we build a a, s- a set of sets that we want to test them out on. And guess what? You said it's just multiplying and adding. Guess what some sets and product sets do? I wonder. But yeah, a lot of GPU stuff later. I think this is still not great usage of that, but oh, I didn't get results either because of the yeah. But I think I can show you this. So this was like our boring version of the results. Oh, it didn't show the time. This one, this one I remember took 12 hours. And I was at UCLA at the time, and because this fucking computer is so loud, I just roll it out on the library and just sleep on the library. I just wake up and I watch it slowly ticking up. At least I have TQDM at the time, so it's like, I know it's 12 hours. But it guess, yeah. Oh, there it is. Only 11,780 seconds. That's not as long as I thought. Oh, the whole thing probably took 12 hours and just, yeah. But what I wanted to say is you made, I don't think my code was written that well, but I think because I bugged out and I lost all of the data, but I think this one only took me 1,100 and I mean it was like 40 minutes, so 2,400 seconds. So if we ever wait, no, it's bigger than this. Oh wait, yeah, no, this one is like 800 seconds because we did until 131 million, which is 2 to the 23rd, 20, 2 to the no, there's always 2 to 20. It's basically four times bigger than this. It was like 40 minutes. So you know what? Thank you. Now I know to use this technique to not kill myself. But there you go. That's it. That's thank you for teaching us CUDA, I guess.
Thanks for watching. Yay. Okay, I'm gonna hit end on the recording.